This is the sixth class of photoelasticity. In the last class we discussed about the different compensation techniques, and now we are discussing about the calibration techniques. Okay, this is the calibration techniques. Why we have to make the calibration techniques? Because we have different types of materials. Okay, so for the different types of materials, we should require an equation. Means we have to compare the standard equation of a material or a specimen to the optical stress optic law. Okay, so if you want to compare it, you require the calibration. So that for the calibration you require the equations. Okay, so for that the photoelastic material has to be calibrated to determine the material fringe value. The sigma value should be determined to so as to convert the fringe order into stresses. So there are fringe orders which are obtained on the whatever the final view, and that fringe order should be converted into stress. Means we have to determine at which fringe order what is the stress value. Okay, so for that we require the calibration. The following methods may be used to calibrate the photoelastic model. So first we consider the simple tensile specimen. So in the simple tensile specimen, how it's going to be there. Okay, see here, this is the simple tensile specimen. It is rectangular, it's having width W and thickness H. Okay, and you can see this load versus fringe order the graph with respect to you will get one curve, linear curve, and you have to take the slope for the calculation purpose. Okay, see here how you are going to make it. Here if we prepare a simple tensile specimen as shown in figure, whose width is W and thickness is H, then under the load the uniform stress in the test specimen, what we do, we will apply some load for here. We have general equation. Generally stress is equal to load per area. So in here the load is applied, that is taken as capital P, and area is considered as W into H. Okay, width into thickness. So the same thing in here, sigma 1 minus sigma 2 is equal to load by area. The load is capital P and area is taken as W into H, that is width into thickness. Okay, so like that we are going to get in here. Means there is only sigma 1 in here, sigma 2 is not there. So for that then sigma 2 is equal to 0. We will consider there is no sigma 2 in here because only one direction load is applied in here. Okay, apply the stress optic law. So we know the stress optic law, that is sigma 1 minus sigma 2 is equal to n sigma f by h, where n is the fringe order, sigma f is the fringe value, and h is the thickness of that whatever the model. So what we do, we know the value of sigma 1 minus sigma 2, that is in here p by wh. We will substitute in here, p by wh is equal to n sigma f by h, but we require sigma f value. Sigma f value should be determined. So the sigma f is equal to, if you just take this sigma f in the left side, and if you take this all terms in the right side, we are going to get the equation as sigma f is equal to p by n 1 by w. Okay, the h's get cancelled out in here, and remaining term we are going to get as p by n 1 by w. So this is the final equation where you can determine the sigma f value. So the sigma f value is considered for the calibration purpose. Like that you have to calibrate the tensile specimen. Next we move on to the beam under a pure bending. In here we are going to consider the beam element. Okay, so in here see this beam element which is having the whatever the depth, that is W, and width is equal to H. Okay, the width are you can consider H in here, that is width, and you can see it is a 4-point bending you are going to apply in here. Okay, so there are two loads at a distance of A from the supports you are going to apply. So and the beam is having the length of L. Okay, the beam is having the length small l, and you are going to apply the 4-point bending load. A rectangular beam of thickness h small h and depth W as shown in figure may be used and subjected to pure bending to determine sigma f. Pure bending in a beam may be produced by applying equal load P at a distance A from the ends of the beam of length L as shown. The uniform bending moment capital M. So you have to consider the bending moment in here, capital M, in the middle portion of the beam. So what is the bending moment? The capital M is equal to load into perpendicular distance, the load which is applied and perpendicular distance, that is load into A. So that we are going to consider in your bending moment. Next, we know the stress in the beam equation, that is sigma is equal to my by I. So this is the equation, this is the basic equation you have to remember. Stresses in the beam, that is my by I, where m is the bending moment, y is the half depth of a beam, the distance of outermost fiber from the center, and I is the moment of inertia we are going to consider. So we have bending moment, that is load into perpendicular distance, that is P into A, and y is equal to W by 2, the outermost fiber distance from the center, and h to W cube by 12 is the moment of inertia, where h is the thickness or breadth and W is the depth. So hw cube by 12, you have to substitute here. You have to simplify that to cancel out this 12 and you will get to 6, and W cancel out the W cube and you will going to get the W square. So this term is going to be obtained for the sigma 1. Sigma 2 is equal to 0 in here also. There is only one directional load is applied, so you are going to consider sigma 2 is equal to 0. So what you do, this term is going to be substituted in the stress optic law. Okay, 6 PA by HW square. If you take 6 in the numerator, it will be 6 PA by HW square. You can see that same equation, 6 PA by HW square, which is equal to N sigma F by H. This N sigma F by H is nothing but sigma, the stress optic law equation, that is sigma 1 minus sigma 2, which is equal to N sigma F by H. So again simplify this, you require the sigma F, you take this to the right side and all others left side. Sorry, this should be taken to the left side and all others to the right side, and sigma F is equal to P by N 6A by W square. How you are going to get the equation? It's nothing but HH get cancelled out in here and all other terms should be written in a appropriate order. So you will get the sigma F. So by that the bending moment, whatever the element or beam is also being calibrated by this equation, okay, by determining the sigma F. And you are going to plot the graph. You are going to plot the graph with respect to load and fringe order, and you are going to take the value of that and you substitute in this equation and you are going to get the values in here. Okay, you get the non-escaping type of fringes. You can see this diagram. So this is epoxy material and one more is polycarbonate material. You can see this dark fringes which are obtained in a pure bending condition of a beam, and you can see these are the concentration points of load where the patterns, the fringe patterns are quite more compared to here, and it will be coming at a bigger fringe orders in here. Okay, you can see there is a lot of stress at here and compared to this portion. So similarly in the polycarbonate you can find a different type of stress with respect to the material property. The stress value is going to be changes here. So these are the patterns which are obtained on here. Okay, so last calibration material is a circular disc, okay, under diameter compression. So this is the circular disc which is hanging the diameter capital D, and the thickness of that whatever the disc is small h, and it is applied diametrical load of capital P, and the stresses which are obtained inside in the axis of x and y, it is sigma 1 and sigma 2, and similarly P by n graph is going to be considered. Okay, similarly the circular disc of diameter D and thickness h as shown in figure, which is subjected to just a minute. Okay, is subjected to a diametrical compressive load P, and the stress along the horizontal diameter as given. So how we are going to take this stress? You have to see this stresses. It is obtained in the design data handbook. This equation is obtained in a design data handbook, so you have to remember this equation. Okay, this is sigma x is equal to the stress in the x direction is taken as sigma 1, and this will be taken as 2p by pi h d into d square minus 4x square divided by d square plus 4x square whole square. You have to remember this equation. Similarly sigma y, the stress in the y direction, it is equal to taken as sigma 2, which is equal to minus of 2p by pi h d into 4d to the power of 4 by d square plus 4x square into 2 whole square minus of 1. Okay, and the shear stress is considered as 0 in here. So if you take sigma 1 minus sigma 2, you will get this form of equation, that is 8p by pi hd. What we consider just x is equal to 0 in here, means x is going to be 0 at the center. Okay, at the center x is equal to 0. So what is the stress at the center we are going to consider? If we consider x is equal to 0, this term is going to be taken as 0, or means this 4x is 0 and this will be 0, d square by d square, it will cancel out, and you are going to get 2p by pi hd. Similarly in here, if you substitute x is equal to 0, you are going to get this term 0, and if you simplify this, it's also going to get 1, and it will be minus of 2p by pi hd. So like that the term is going to be taken, and 8p by pi hd is the value if you substitute x is equal to 0 in here. Okay, like that it will be there. So similar equations here, if x is equal to 0 at the center, the equation going to be changes here, that is okay, just a minute. This is sigma 1 is equal to 2p by pi hd, and sigma 2 is equal to minus 6p by pi hd. Okay, so like that the equations are going to be considered. Sorry for the inconvenience, some technical problem is here. Just a minute. Okay, this sigma 1 is equal to 2p by pi hd, and sigma 2 is equal to minus 6p by pi hd. If you take sigma 1 minus sigma 2, this form, you are going to get, if you simplify this, you are going to get 8p by pi hd, which is equal to n, you are going to get, and you just substitute this stress optic law, means sigma 1 minus sigma 2 is also equal to n sigma f by h in the stress optic law. If you equate these two values, and you have to determine the sigma f value, say this is in here. So by properly cancelling this h value, we are going to get the value of this equation, that is sigma f is equal to p by n 8 by pi d. So this is the equation for the circular disc under the diametric compression for the determination of fringe value, that is sigma f. By knowing the value of p for the particular fringe order n at a center disc, a graph can be plotted. So if you know the value of load, if you know the value of fringe order, you can just you can plot the whatever the graph whose slope is substituted in the equation to determine the value of sigma f. Okay, like that you can determine the sigma f in here. You can see this fringe pattern in the circular disc. The load is diametrical load is applied at its point. So you can see the fringes are more at the point of load, and it will travel along here, and it will move to the perpendicular direction. The fringe pattern in the disc is shown in here. You can see this is the zero fringe order, means we will take n value, means the first fringe which is generated and it will move to here, it will be taken as 0, and this will be second, this will be third, this will be fourth, like that the fringe order going to be increases. Okay, so if you want to determine stress at here, for example 3 or 4, what you have to do, you have to consider this 4 as a fringe order, and you have to substitute in the graph value, you know the load value, and you have you know the fringe order, and substitute that in the equation, and you can get the sigma f value. So by that you can determine the sigma 1 and sigma 2 values in here. So this is the pattern of calculation in the circular disc. Okay, so this is all about the calibration techniques. Thank you, students. This calibration techniques is also very important as per exam purpose, and also regarding the understanding of the photoelasticity. So try to work out these calibration techniques. Okay, if any queries, you can message me or call me for clarity. Okay, thank you, students. Bye.